All right, welcome back. So today we'll be looking at direct current circuits. So sometimes the circuit could be complicated, but we'll start from the simple one to build up upon, and then we'll get a little bit more complicated scenarios in this chapter. So first, if there's a DC circuit, then there will be a direct current power supply. So in many cases, we'll be looking at the battery as the power supply. For battery, we know that there's potential difference across the terminals. So this is something just like if you add two different location of height, then there should be gravitational potential difference. So in the figure here on the right, you'll see that the water can go from a higher location to a lower location. So its gravitational potential energy can be converted into mechanical energy. The same here for battery. Across the terminals, the positive and negative terminals, there's electric potential difference. Okay, so that difference in the energy informs electric potential energy can be utilized to power the circuit. So for the potential difference between the terminals of the battery is called terminal voltage, or it's also called electromotive force. Abbreviation for EMF means electromotive force, or epsilon, which looks like E, but it's pronounced as epsilon. So this is a voltage, not a force. Okay, just keep that in mind. For the amount of work done, if you need to take a certain amount of charge delta Q from one terminal to the other, then electric work done is the Q times V, right? V is the epsilon here, and then Q is delta Q here. For battery, it actually has internal resistance, a small one, but there's a internal resistance there. So then if you are given a battery having an EMF, say 1.5 volts, so then it will supply a little bit less than the 1.5 voltage to the circuit because there's potential drop across the internal resistance. So typically you might be, if your battery is brand new, if it says it's 1.5, say whatever volts, 1.5 volts, then if you directly measure it, it could be like 1.53. So to just to get the voltage close to the 1.5 as specified, okay? So then the voltage from the terminal is equal to epsilon, which is the specification of the battery, the EMF minus the current for the circuit, and times the resistance of the internal resistance of the battery. So the current through the voltage will also go through the battery in that sense. All right. So this could be a schematic drawing of the battery in the circuit. So then what it will look like if you include internal resistance, okay? All right. So there will be a drop of the delta V due to the internal resistance as supplied to the voltage across the circuit. So again, this figure shows you the effect of that internal resistance, okay, that's to the whole circuit. Let's take a look on the first example here today. It says a 12.0 volts EMF automobile battery has a terminal voltage of 16.0 volts when being charged by a current of 10.0 amps. What's the battery's internal resistance? So in this case, it says the current going through is 10, right? And it has a terminal voltage of 16, but its EMF is only 12. So then it's something like this. Let me show you on the paper. So this is being charged, but here is the terminal. There's an internal resistance, and then there's this battery voltage, which is 12.0, but across these two terminals is 16 volts applied. And as a result, there's a 10 voltage current. So 10 voltage current, and it's asking you for first the internal resistance. Okay, so the 16 volts then should be equal to the 12 volts, right, plus the current times this internal resistance, I times R. Okay, So then you can calculate what be R will be 16 minus 12 and divide by the current of 10 amps. That will be your R. Okay, so this gives you 0.4 ohms as your internal resistance. Okay, for your part A. Now part B, what power is dissipated into the battery? So the power dissipated on a particular element is equal to, you can use one of the equations you can do. So P equal to I times V, or I square R, or V square over R. So in this case, we have I and R, we can just use I square over R, or I square times R. So it's 10 amps squared times 0.40 of the resistance we just calculated. So it's 14.0 watts. Okay, so as you charge it, the power dissipated for the battery is that much. C is asking you at what rate in degrees Celsius per meter or per minute. Will its temperature rise if the mass of the battery is 20.0 kilograms and it has a specific heat of 0.300 kilokelvin times kilogram times degrees Celsius, assuming no heat escaped. Okay, so all the heat dissipated increases the temperature of battery. So let's take a look on here. So it's asking degrees per minute, right? So we can do P times delta T, which gives you, that's the heat, which is MC delta T. Okay, so you are looking for, actually you are looking for degree per minute. That means delta T over small t, where small t is in a minute, right? So that equals to, in this case, from this equation, that should be equal to P over M times C. Okay. All right. So in this case, this is going to be 40 watts divided by 20 kilograms times 0.300 kilokelvin times kilogram and degrees Celsius. Well, this guy should be multiplied because this is calorie, right? But we need joules. So then multiply by 4.186 kilojoules. So kilojoules over kilocalorie. Okay, so in the case. So this delta T over time T then is equal to 0.00159 degrees Celsius over SI unit will be per second. Now it wants in degrees per minute, so that means you multiply by 60 seconds in 1 minute. Okay, so that gives you 0.0956 degrees Celsius per minute. Okay, so there's a little bit of the conversion here. Okay, so let's go back to the slide. All right, so next, so we have to look at battery. Next, take a look at the resistors, if they are in series or in parallel. So this is similar to capacitors in series in parallel. So when the resistors are in series, they actually share the same current, which current is equal to charge over time t. So it's like saying they share the same charges over the same time. Okay. And then when they in parallel, then they share the same voltage. So this is again the same as the capacitors in parallel. All right, so let's take a look at when the resistors are in series. So when they are in series, you can treat, for example, if you have 3 of them, you can treat 3 of them as equivalent capacitor. So one single capacitor as combination of those 3. So then in that case, they share the same current. So the current I1, I times R1, I times R2, I times R3, okay? Potential across each of resistors add up should be equal to the potential by the battery. So unless otherwise indicated or specified, we will ignore the internal resistance of the battery. So in this case, it will be equal to V. So V equal to I R1 plus I R2 plus I3. Now, as the 3 is treated as 1, so then I times R EQ should be also equal to the V. Okay, so you can write like I times R1 plus R2 plus R3 equal to I times R equivalent. Okay, so then R equivalent will be equal to R1 plus R2 plus R3. Okay, so that means summation of the R's in the circuit. So if you have 2, just R1 plus R2. If you have more than 3, then add the remaining resistors resistance up. Okay, but this is similar to capacitors in parallel. So they are flipped, right? In series for capacitors, or in series for resistors is the same in for capacitors in parallel. Excuse me. All right. So then when the resistors are in parallel, so then that's similar to the capacitors in series. So in that case. So here, V across each resistors will be the same. Okay, so then we'll be looking at the current. So current goes through split into I1, I2, and I3. So I1 plus I2 plus I3 should be equal to total I. Now, I1 is equal to V over R1 because R1, R2, R3 are in parallel, so they all have the same voltage V. So V over R1 plus V over R2 plus V over R3 is equal to V over R EQ. Okay, so V is the same, will cancel, so then you'll get like 1 over R EQ equal to 1 over R1 plus 1 over R2 plus 1 over R3. So this is similar to the capacitors in series then, okay? So then that equals to in summation of 1 over R. When you want to calculate Req, then you do inverse of each capacitors add up and yeah, and end take an inverse one more step, okay? So let's take a look at this example here. It says if you are given a 48 volts battery and you have 2 resistors, you can connect them in series or in parallel. So what would be the what would be the current and power for the circuit? Okay, and then what will be the current and power for the circuit when they are in, so first one in series, the second one when they are in parallel. All right. So let's take a look. We can sketch this one by drawing the figure here. So when they are in series, right? So you have 2 of them, 24 ohms and 96 ohms and 48 volts for the battery. So the current through the circuit, right? So then you can, this one can be treated as the equivalent of the 2 in series. Okay, so the 2 in series. So you should add them up. So 24 plus 96, 120. Okay, and then 48 volts. So the current then will be equal to the volts divided by the resistance. So that gives you 0.40 amps. All right. And for the power will be I squared times R for the 2 in series. So 0.40A squared and times 120 ohms. That will give you 19.2 watts. Or you can do V squared over Req. Okay. Or you can do V times I. They're all the same. 19.2. Okay. Now B, if they are in parallel, so then you have 1 and then 2 in parallel to each other. 24, 96, and then 48 volts. Okay, both resistors in ohms. So when they are in parallel, so then it's equivalent to just a single one, but equivalent of those 2 in parallel. So then that will be 1 over 24 plus 1 over 96, right? And then inverse. So that gives you 19.2 ohms. So then for the current through the whole circuit, you'll do 48 volts divided by 19.2 ohms. Okay, so that will be 2.5 amps. And then for the power, again, you can do I square over R, V square over R, or V times I. So either way. So we'll do V square over R then this time. So 48 volts squared divided by 2.5 amps. Okay, so that gives you 120 watts. Okay. All right. So let's go back. Now, many times your resistors not are just in series or in parallel. So they could be part of the circuit could be have resistors in series or in parallel, but then that part will be in series or parallel with another part, and etc. So combination of series and parallel. So in this case, you have 7 ohms here, 10 ohms, 6 ohm, and 4 ohm. So if you have a complete combination like this, you'll be looking at just one part or maybe several parts of the circuit individually and see if they just have resistors in series or just in parallel. So in this case, it looks like these two, 6 and 4, they are in series. Okay. So then you treat those two together. So the combination of these two gives you 10. So then now the circuit becomes this guy. Okay. So 7 and then 10 and then with another 10. But this combination, the 10 is in parallel with this guy. So you treat these two together, okay, when they are in parallel. So 1 over 10 plus 1 over 10 and inverse of that gives you 5. So then this part then be replaced by a resistor of 5. Okay, so this part was replaced by a resistor of 10 to be this case. Now this part becomes resistor of 5 in this case. And these two are in series, so you add them up to be 12. Okay, so then the overall equivalent will be 12. Okay, so just look at each part of circuit carefully and then identify the ones they are just in series or in parallel and replace that part with an equivalent resistor and then start that from that point on doing over it again until you reach to the end. You only just have one equivalent resistors for the whole circuit. Okay. All right. So let's take a look on this one. This one says consider the circuit showing the figure, calculate the equivalent resistance of the circuit. Okay, and then B, calculate power consumption of 6.2 ohms resistor. Okay. So let me sketch the circuit here. All right, 11 ohms, 7.5 ohms, 6.2 ohms, 12 ohms. Okay, and 15 volts across the terminals of the battery. All right, so as we check on this one, it looks like the 6.2 and 12 are in series, right? So you add those two up and then it becomes 18.2 ohms. So this part will be replaced by just the single 18.2 ohms. So then this becomes 7.5, but then 18.2 ohms, 7.5 initially, and this is the 11 still there, okay? So we look at this second circuit and then we figure, okay, these two are in parallel, just in parallel. Okay, so then these two will be treated as one. So 1 over 7.5 ohms plus 1 over 18.2 ohms. And then inverse of that should be equal to 5.31 ohms, 5.31 ohms. So then this part will be replaced by that. So this becomes then, okay, 5.31 and then 11. 5.31, 11. So these two now just in series, right? So then you will add them up. So that becomes just a battery connect to a simple equivalent capacitor of the everything 16.8, 16.31, okay? All right, so then the equivalent resistance for the whole circuit will be this guy. Okay, so for part A, Req be equal to 16.31 ohms only. Part B is asking you what will be the power consumption of this resistor. So you need to find what will be the current on this guy or voltage. So either way, let's take a look on the current. Okay, so the current goes through this one from the battery's positive terminal, comes out, and then it looks like it splits into two, right? So I1 and I2, and this is the total current, I total. All right. So in order to find the current here, we probably need to find what will be the voltage across. Okay, so the current I2, or you can look at this one. So I2 here, and then I1 here, and then the initial I. Okay, so you can figure out, if you want to figure out I2, you'll need to know what will be the voltage. Okay, for these two in parallel, or just this guy, right? Voltage across the equivalent should be the same as the voltage across each of them. All right, so to find the voltage across this, so you'll need to find either the voltage across this one, right? Or the current across the whole thing. Then you can do current times this one will be the voltage. So it looks like either way, if you need to find voltage across this one and then 15 subtract that voltage off to be given this voltage, you'll still need to know the I through this guy. So it looks like you need to know the I of the whole circuit. I of whole circuit, you can actually use this final circuit because the whole circuit has that resistance. So then I total is equal to the 15 volts divided by 16.31. Okay, so that gives you 0.92 amps. Now the easy way to do is use that 0.92 because that's the current in the circuit. So cross this guy as well, right? So then V across the part that is parallel is equal to, and that's called the A V between A and B, I think, in the circuit. So that's this A and B point there. Okay, so A and B, or A and B here, A and B. Okay, so will be 0.92 amps times the 5.31 ohms, 4.88 volts. Okay, so for the voltage across the combination here, which is the same as each of the voltage on each of them. So then current I2, you can directly calculate it. It's going to be this voltage, 4.88 divided by 18.2. Okay, that's I2. So 0.269 amps, and that's across this resistor, which is a combination of those two. So then I2 for each of them is that. So then the power for the 6.2 ohms is equal to I2 to the square times R of the 6.2 ohms, okay? 0.269 and squared times 6.2 ohms. Okay, so that gives you 0.45 watts of the power consumed by that 6.2 ohms of battery. All right, so going back. Now, sometimes you are not just having one battery in the circuit. So then things becomes a little bit more complicated, okay? Because you are not sure then what will be the direction of the current, because you could imagine like the current goes from one battery positive end and then hit A, right? Now this current could be split into two, but then the current on this guy will go against the direction of that. So depending on which one, they kind of cancel out each other partially, but then what will be the total current in this branch, right? So it could be in this direction or it could be in the opposite direction, depending on which one provides more current from the two batteries. So in that case, we will apply Kirchhoff's rules. And there are two types of rules here. One is the junction rule, and the other one is the loop rule. The junction rule is the consequence of charge conservation. So basically, and that can be translated into the current, right? Charge over time T will be current. And loop rule is conservation of energy. Energy can be translated into potential difference, right? Or potential in that case. All right, now let's take a look at these two rules one by one. So junction rule says at any junction, the current entering the junction must equal to the current leaving. So that means summation of I in will be equal to summation of I out. Or if you have one current in and split into two, so then I1 equal to I2 plus I3. If you arrange the equation, it becomes I1 minus I2 minus I3 equal to 0. Okay. Loop rule says the algebraic sum of the potential difference around a closed loop must be equal to 0. So you're starting from point A and then coming back at point A, right? So there's no change of location, so the potential should be no change. That means summation of potential across each of the elements you encounter should be added up to be 0. Okay. So if you have just two elements, battery and resistor, so then across this guy plus that guy equal to 0. Okay. Now, so in this case, if you apply loop rule, you need a current, right? The direction of current and then the direction of loop, okay? So when you apply junction rule, depending on how many junctions you have, you could have a few equations, and then you have a few equations also from the numbers of loops you could have, right? So if you have two loops, you have two equations based on loop rule. So using these two rules, you can write as many equations as you needed to solve for the problem. So if the problem is looking for one unknown, then just use one equation. And then if the problem is looking for two unknowns, then just two equations will be enough. Now I should mention that these equations should be independent of each other. So that means they are not the same equations, right? So if you have two same equations, then it doesn't help. You just count as one. They just count as one, okay? All right. So let's take a look on this example here. So we'll be using the same circuit, the same problem, but let me take a look on, yeah. So we'll take actually two of them. So the first one will be the same as the one just we looked at before, but because there's only one battery, so you can actually do what we did here, right? And then solve for that. But because there are multiple loops in this one, so you can also apply Kirchhoff's rules, because then you can actually have a couple of loops and then there's junctions there. Okay, so you can apply that and then also work for this one. So it's the same problem, but we are using Kirchhoff's rules here. So let's take a look on how we actually solve that, use Kirchhoff's rules. All right. So this battery here, 15 volts, this junction number B junction, and then there's these two resistors. There's this A point, there's another resistor here, there's another resistor here, okay? So this is 11 ohms, 7.5 ohms, 6.2 ohms, and 12 ohms, okay? But this time we are just looking for the current through each resistors and then the consumption of power of this one again. All right, so there will be this current. Let me now just call it this I1, because this I1 will split into two. Oh, this is I2 now. Okay, that's fine. So we can use that. This is I3. Okay. So this junction, and then you can see the current. So this guy's 15 volts. So the current I2 will go into this one, and then I3 goes through this two and comes here, I3, I2, and then we'll merge, right? The two will merge. Now becomes I1 again. So these two junctions are the same junction. They gives you pretty much the same equation, right? I1 equal to I2 plus I3, or I2 plus I3 equal to I1. So they are the same. So that means there are two junctions, but they are identical. So you can just pick one of them. So you can say I1 equals I2 plus I3. So that's your first equation. Now you need two more equations because you have three unknown to solve for. So you'll pick then two loops. So you put this loop here on this side. You'll take another loop here. Now I should say the starting point or the assumption of the direction for the loop. So loop number one, loop number two. Direction of the loops will be arbitrary. You can pick this one, the clockwise as your loop, or you can direction of your loop, you can pick counterclockwise. The same applies to the direction of the three currents you choose. Okay, so it could be arbitrary originally, but typically the current going is starting from the positive side of the battery and then through the circuit coming back. So we'll, in this case, we'll use that. But direction for I3 and I2, then it doesn't matter. Once you have more batteries in the circuit, it could be different. Okay, so but at the end, if your number is negative, that means your original direction of current is not picked right. So you just reverse that direction. So nothing significant there. Okay. All right. So for the two loops, so let's start with the so we probably can start with point B. Okay. So for this loop one, so here are the things. So if your directional current and loop going through the same element are the same. Okay, going through an element, your directional current and direction of loop are the same, you get potential drops. Okay, so that means minus. So minus I2 times 7.5 ohms. Okay, and then the second one here, now I2 comes in here, but it comes as I1 in this loop. So then I1, the same direction of the current going through 11 ohms, and then the same direction for the loop. So that's again minus. Now I1, 11 ohms. Okay. Now across the battery, if you go from negative terminal of battery to the positive, then a potential increases. Okay, so that's plus 15 volts. And going back to point B, that is equal to 0. If you are going from the positive terminal of the battery to the negative terminal, then you get negative. So you between minus 15. Okay. So that's loop one. You are back. For loop two here, so again, we can start from point B, but goes through this loop and coming back. Okay. So I3 and loop two going through 6.2, they are in the same direction. So again, you get minus. But I3, 6.2 ohms. And then the same for 12. Okay. So minus I3 of 12 ohms. And on the 7.5, so the current will be I2, but goes in the opposite direction of your loop. So current and loop are against each other. So then the voltage increase. Okay. 7.5 ohms. So that goes to 0. So you have three equations you can solve for the three unknowns. Okay. So the trick here is to write one, or actually you will be just looking at the three equations, examine the three first. So this one has I2 and I1, and this one has I2 and I3. So you probably will, if there's one unknown for all the equations, in this case will be I2, right? I2, I2, I2. So then you write the other two in terms of I2 from here and there first. So from here you get I1 equal to, you arrange the equations. So basically you get 15 minus 7.5 I2 divided by 11. And then from this third equation, you'll get I3 equals to 7.5 I2 over 18.2. Then take this back to the first equation. Okay, so you'll get I1, 15 minus 7.5 I2 over 11 equals to I2, okay, plus I3 will be 7.5 I2 over 18.2. All right, so then now you have one equation that just have I2 in it. You rearrange the terms, you'll get I2 equals to 6.51 amps. All right. And then now you'll take that into I1. So you'll solve for I1 equals to, so I2 goes in there. Okay. It gives you 0.92 amps. And then again, I2 goes in there, gives you I3. So I3 equals to 0.27 amps. Okay, or 0.269 amps. So 3 sig fix maybe. Okay, so the currents through 3 resistors. Okay, so this is 0.92 is for the 11 ohms, 0.269 is for the 6.2 ohms and the 12 ohms. Okay, this guy is for the 7.5 ohms. Okay, and the power consumption for that guy for the 6.2 will be I3 square times 6.51 or 0.62 ohms. Okay, so the 0.269 amps square 6.2 ohms, that would be equal to 0.45 ohms, just as what we had earlier. Okay, so if you look up there. All right, and one more relative simple one here. So it says consider and the circuit showing below, find V1, I2, I3. Okay, so it tells you some different numbers there. If you look at the slide, go back to the there. All right. So you have 3 unknowns, and then you have you have 3 unknowns to find. So you'll pick actually. So there's 2 junctions. They are the same in the problem. Okay. So you'll pick 1 junction and then 2 loops. Okay. So the first loop on the left hand side and then the second loop on the right hand side. So let's stick with that. So again, then you'll get the first equation of as I1 plus I2 equals to I3 because I1 and I2 goes in and then I3 comes out. Okay. The first loop on the left, let's start with the positive terminal on the battery. Okay. And let's go again clockwise. So then minus I1, R1, okay, plus, in this case, for R2 and I2, the loop goes in the opposite directions. Okay, so then that's plus I2, R2, okay, and then now V1 plus V1, that goes to 0. Okay, now for the second one, the second loop on the left-hand side, let's start with maybe somewhere just bottom of the R2. Again, clockwise direction, so minus I2, R2, and then cross the battery, so then plus the V2, okay, and now minus I3, R3, that goes to 0. Okay, so you have those 3. Now we'll plug in the numbers. I1 is 2, so 2M plus I2 equals to I3, okay? And then the next one will be, so I1 times R1 minus 2 times 12, okay? Plus I2 times 6, so 6I2, okay? And then plus. V1 equal to 0. Okay. The last one will be minus 6I2 again, and then plus 21V and minus I3 times R3. R3 will be 5. So 5I3 goes to 0. So you have those two equations, and then you can solve for the three unknowns. So I'm not going to repeat the algebra, but at the end, I2 is equal to 1 amps, and I3 is equal to 3 amps, and V1 is equal to 18 volts. Okay, so that's the final result. All right, and then we'll stop here for today. We'll actually come back another time for the reminder of this chapter here. Okay, so see you guys.